I'd like to welcome you to today's Multifamily Upgrade Program webinar series. Our presenter today is Scott Blunk from Partner Energy, and I would like to hand it over to Scott to begin the webinar. Scott?
All right, thank you, Stephanie. Welcome back, everyone. If you attended last week, this is the second in a series of webinars going at a higher level over the single-family building analyst information. That's me. You're welcome to email me if you have any questions about anything you see in the training. And then there's Mike, who is the technical manager, or who is a technical manager at TRC and is running the PG&E Multifamily Upgrade Program. So you can email him if you have any questions about the program. Okay, so there's two kind of series of webinars going on. One is the EnergyPro technical webinars. We've had 3 and there's 2 to go. These, the ones that have passed are on the YouTube channel, and I'll show you that in just a second, but there's 2 coming up next Wednesday, and then a couple Wednesdays after that. Architectural building features will be about overhangs and side fins, slab area perimeter, just the architectural features and how to model them in EnergyPro. All EnergyPro focused, and focused on EnergyPro 5, since that's what the program's using right now. And then today, this is the building analyst topics. Like I said, last week we did building science. This week we're going to talk about the building envelope. And of course, they're all building science, but that was kind of more the science-specific measures. And then, so then it goes on roughly every 2 weeks after this until actually late in August is when we finish up. And we finish up with a diagnostic training, which is a full day on August 20th. So that'll be some classroom training, some field training to help prepare you to take the BPI analyst exam. We will give the written exam on the 21st. The 21st, the exam's only a couple hours, so there'll probably be a couple hours of training review for the exam, and then the exam. That training will occur at the PG&E Energy Training Center in Stockton. So the 20th and 21st. Just mark your calendars. Hope to see you all there. And also just to let you know, more information will be coming, but seating is limited, of course. And so we're taking basically the reservations or whatever. You can get your spot in that class by sending money for the BPI written exam. Kind of that'll hold your spot. But we'll get you more information. We're a couple months away still, so no rush right now. And as I said, more information is coming soon. So the program has its own YouTube channel shown here. So this webinar will be on the YouTube channel soon, as well as the EnergyPro webinars that are anything that's already passed is on here that we've presented. So the EnergyPro tech topics and then the building science webinars are all going to be on this channel. It's a pretty, I searched there PG&E Multifamily Upgrade Program, and you'll find it very quickly. Easy to find. So you can review this one or ones that you've missed. So what this training is it's not a substitute for the 5-day course. This topic, this certification class is typically 5 days, 5 classroom days long, and then some certification exams. This is kind of meant as an introduction for people who are maybe new to the field, so so it serves as an overview. And so, or if you're in the field and maybe you're a HERS rater, or you've been performing other duties, modeling or whatever, but you don't have your certification, this should help you understand what is going to be on the BPI analyst exam. So for people who have a lot of industry knowledge, this could is just serving as a refresher. It's not a substitute for studying on your own. I do recommend that you spend some time outside these webinars to study and prepare for the exam. I can't teach you all 5 days in 5 or 6 90-minute webinars, but I'll do my best. The best study material, or one of the best study aids, is going to be the Residential Energy book by John Krieger. Saturn Energy is his company, but it's in its, I think, 6th edition. You can get a 5th edition probably really cheap on Amazon. There's very little change in the books, but it's a great book for residential energy purposes. And I'll be giving you more resources for that coming probably next time I teach. All right, we'll get going on today's building envelope. This is a 90-minute webinar. It'll take probably all 90 minutes. So I'll do my best to be moving through this. But before I get started, last week there was a lot of questions about basically what you can do with this certification. And so assuming you take these classes and you pass the written and the field exam, you're then a BPI building analyst. And it's actually not a multifamily analyst. It's really a single family certification, but it's applied in multifamily. And so what you're able to do is you're able to do essentially all combustion testing on single family, on multifamily low rise, and multifamily high rise. If you want to become a rater in the program, this certification is one of the certifications that will help you get into the program as a rater. This certification, if this is the only one you have, it will limit you in terms of you can't do high-rise multifamily, but there are fewer of them out there. The bulk are low-rise, so this is kind of your entry point. There are other requirements, insurances and stuff like that, of course, but this certification will give you some of what you need and help get you on the list. But it's actually not a BPI multifamily analyst class. It's a single family, or just a building analyst is what they call it. So with that, so today's about the building envelope. So we'll talk about some structural systems, the envelope, thermal bridging, R values, some insulation and inspecting it, air leakage, and just some typical wall assemblies and their function. All great stuff today.
Hey, Scott.
So, yep.
Can I jump in and just do one housekeeping thing? So I just want to remind all of the attendees that you are in listen-only mode, and if you have any questions, please type them into the chat, and we will answer them as best as we can. And also, I just want to remind everybody that this course is eligible for BPI continuing education credits. At the end of the webinar, you will be prompted to fill out a short survey and enter in your BPI number, and we will report that to BPI on your behalf if you'd like. If not, you can just self-report to BPI. So just a reminder, please fill out the little survey at the end and indicate your BPI number if you'd like it reported to BPI. And that's all. Thanks, Scott.
Thank you, Stephanie. Yeah, so after kind of each module in this, I'll be pausing. I should have paused already, but thanks, Stephanie, for stepping in. And Stephanie will read questions, and we'll do our best to answer them while we're here. And so, yeah, your BPI number is important if you want BPI CEUs, or at least you would like us to apply for you to do them. It's always nice to have somebody else do your work. But you have to be certified already to get BPI CEUs for it. So these CEUs can be used for other things, maybe Greenpoint rated, AIA, maybe, I'm not sure, but they are available for BPI CEUs if you need them, if you're already certified to. Okay, building envelope. So kind of a list of what we're going to be talking about today: air pressure boundary, the blower door, thermal boundary, some building assemblies, and roof inspections. And I actually took out moisture intrusion, so we won't cover that today. It was just running long, and I didn't want to go over again. Do my best to keep it short. The building envelope, it's also called the shell. It's about where, you know, it separates conditioned space to unconditioned space. And then there's things like the pressure boundary, the thermal boundary, or the thermal envelope, and the building envelope, or like this picture is showing that the building envelope is different than the thermal envelope. And that's just that the roof is part of the envelope that's separated from the insulation. But typically it's going to be the walls, the roof, and the floor. So the components of the envelope, the shell is comprised of the roof shingles, you know, the stucco, slab doors, and windows. So all that is the shell. The thermal boundary, when we use that, we talk about where the insulation is. So the thermal barrier, it is where, if there's no insulation there, it's where the insulation should be. So you've got an uninsulated wall where there's really no insulation, but we'd still call that the thermal boundary. It's doing its best it can without insulation. And then the pressure boundary, you can kind of think of it as the skin of the balloon, but it's really what surface is stopping air from leaking in or out of the house. That's called the pressure boundary. It's important that the pressure boundary be continuous, so there's no gaps in it or holes. And when we talk about infiltration or air leakage, we're always working on the pressure boundary. And then there's the vapor boundary or vapor barrier, and that's used to keep the bulk moisture out of the building. So a lot of times it's called a vapor retarder in the field, but it would be like the Tyvek. Tyvek on the side of the house is breathable. It lets in air, but it stops the bulk moisture. And a breathable wall assembly is still good. We want it to breathe, but we don't want the bulk water to get into the envelope. Okay, so the envelope design, pretty much everything that's built these days, at least low rise anyway, is built using a platform framing. Each story of the building is built individually and placed on top. So it's just kind of, you keep doing the same thing over and over again. There's a floor a unique floor that can be separated, it's not integrated into the wall assembly. There are other types of framing, of course. There's balloon framing. So balloon framing is where like a stud could go from the first floor to the top of the second floor. Like one stud goes all the way up. That's how houses used to be built. There's some issues with building science issues with it, but we don't really see it anymore. It's going to be in older homes, probably pre-1950, pre-40 maybe. And then there's other types of framing that you just won't see much, but typically we're talking about platform framing. And that's, they build a platform and then the walls, another platform, another set of walls until you get to the roof. And the building envelope, like a wall assembly that's shown here, is comprised of a lot of different elements. And we'll go into those in more detail later on, so I won't spend the time on it right now. And then we'll go into the pressure boundary, but I'll pause for a second to see, Stephanie, if you've got any questions or anything that we should address at this point.
Scott, there are no questions at this time.
All right, great. It's a short section. Hopefully it's all well understood. So the air pressure boundary, talk a little bit about air leakage, stack effect, some roof construction, air barriers, and air sealing. So we talk about pressure boundary, and again, this is the skin of the balloon. This is what's holding the air inside the house. What we really want is for it to be continuous, so no gaps, right? Airtight, so that we don't let air go in or out of like a wall or a roof or a floor assembly. And we always want our pressure boundary to be aligned with the thermal boundary. So that is, the air stops maybe on the side of the drywall. On the other side of the drywall is our insulation. That's what we're talking about with pressure boundary aligned with our thermal boundary. That is the most effective way to build, and that is what you always want to see. And, you know, on the airtight piece, there's several things going on, and we'll talk more later, but when air leaks out of a building, so the air has energy embodied inside of it. And if it's in the winter time, it's got heat in it that's going out. So if the air is leaking out of the house, heat is leaving the house. It also has water in the air. And so as the air leaks out of the house, it's taking that water with it, which kind of we talked about last week about dew point. You know, it could cause problems where if the vapor went all the way through the wall or through the roof, no big deal. But if it condenses somewhere inside the wall, then we're going to have a buildup of bulk moisture, and it's really hard to dry out a wall or any enclosed assembly in the building. So that's part of the problem with the air leakage. And then of course there's drafts and stuff, which makes people feel uncomfortable. So just bad all around. So possible areas where unclear where the boundaries are. You know, there's in most construction, just the way the construction industry is, typically behind a bathtub, if it's on an exterior wall, there's an issue with the alignment of the pressure boundary and the thermal boundary. Because after you're done framing and the rough plumbing's in, you typically the bathtub goes in and is set in place. Hopefully after the insulation, and so there's insulation in the wall. Then you put the bathtub, and then you put the drywall. But the drywall wouldn't go down behind the bathtub. So now the air barrier or pressure boundary would be the bathtub itself, but the thermal barrier or thermal boundary would be the wall where the insulation is. So that's typically a place where we find that the two are not aligned. It takes a special contractor to actually six-side was what we call that. So it's where you put the pressure boundary on the wall and not make the bathtub the pressure boundary. Other areas would be typically chimneys. Modern day chimneys are just a wood framed appendage to the house, and so there might be insulation inside this wood framed chimney, but there wouldn't be an air barrier on the inside of the chimney. It would be like the drywall where the chimney's surface of the wall inside. And since I mentioned that six-side, what we want for all vertical insulation is 6 sides of contact with the insulation. So in a stud bay, that means the insulation should be touching the top, the bottom, the right side, the left side, the front, the back. That's the 6 sides. So that doesn't happen in places like the chimney and the bathtub, and then also knee walls. That's the other place where that's happening. All right, and a very fuzzy picture of some pressure boundary So what this is saying, my cursor, I'll move slowly. So the red could be the thermal barrier and the pressure boundary. So the two could be aligned on the red. Or you could move it over here, and it could be the roof. So if the insulation is put on the underside of the roof, and then there's like some drywall or some other type of air barrier there, you could move the thermal and pressure boundaries could align at that point. Typically it's done more like this, but a lot of times when it's done like this, this piece here, this vertical piece does not have the 6 sides. So it's just an issue in modern construction. So now, you know, a lot of times we're the building scientist community, we want insulation in the roof deck, and with the roof insulation in the roof deck, hopefully there's an air barrier there too, and our ductwork in the attic is now in conditioned space, so it loses less energy. But anyway, that's pressure boundaries and air and thermal boundaries. All right, air leakage. Air leakage is a result of incomplete pressure boundaries. In the industry, a lot of people just refer to it as infiltration. Infiltration is a fancy word for air leaks. Makes it sound more professional, I guess, if we use air infiltration. But to not confuse it, infiltration is really air coming in, right? Exfiltration would be air leaving the building. Air leakage is just air leakage. It doesn't matter what's coming in or out. But those two, you'll often hear the term infiltration used, and not air leaks. But that's what it is. So what's the big deal about air leaks? We talked a little bit about it, but it reduces the R value of the insulation. The point of insulation is the insulation itself, the fiberglass isn't really serving as the insulation. What the fiberglass does is it holds pockets of air, and the air has a greater insulative property than the fiberglass itself. So if air is leaking through that insulation, it diminishes the effectiveness of the insulation. And then of course air leaks also move moisture. If moisture moves all the way out through the wall, no big deal. If it condenses inside the wall, that's when we can create some biological growth in the wall, or otherwise known as mold, mildew, fungus, all that fun stuff. And then air leaks can also, I don't know about dangerous house pressures. Sure, when we talk about CAS testing, a lot of CAS testing has to do with pressures inside the house, and if like a small laundry room with a exhaust fan and a dryer running, and let's say there's a water heater in that room too, the air leaks, which here are mechanical, right? It's still the same thing. It's the dryer and the vent in that room. Those air leaks can cause the water heater to backdraft, which would be the dangerous situation. So don't just think about passive leaks like from wind and other, and just pressure differences inside to outside. It's also the mechanical ventilation in the house. So an air leak is only an air leak if it has 2 things, and that's a hole. Can't be an air leak if there's not a hole, and a pressure difference. Think of the balloon again. The pressure inside the balloon is greater than the pressure outside the balloon. So you put a hole in it, the air is going to leak out. However, if there's a hole, if the door is open in my office right now, but there's no pressure difference between my office and the hallway, so there's not necessarily air leakage through that door. So every air leak needs those 2 things. And then what's driving these air leaks is the stack effect, which we'll talk about in a minute. That's just the pressure. That's just the concept of buoyancy, and hot air rises and cool air falls. And we'll talk a little bit about that. And the mechanical effect we talked about, vents and the mechanical ventilation, like in your dryer itself is mechanical ventilation. Wind effects, we'll talk about all of those. So building in the wind, on the On the side that the wind is hitting, there's going to be a higher pressure than the downwind side of the house. Can't remember, leeward side or something. But so if the wind is hitting you from one side, that's the high pressure. Low pressure is on the other side. So what that's causing is you've got that's the delta P, or the change in pressure that's causing the air leaks. The stack effect, like I said, that's hot air rises, or it's also, you can think of it as buoyancy. Hot air will float on cool air, so it goes to the top. That causes high pressures at the top of the building, low pressure at the bottom of the building. That's your delta P. And then combustion and ventilation air, that's just mechanical ventilation. So it's going to, here on our 3-story house, or house 2-story with a basement, the water heater has a vent pipe. Of course, if the water heater is running, hopefully the exhaust is going out. Well, that's causing a negative pressure inside the house. And so the air has to come in somewhere, and it's going to leak through the building shell and get into the house. This is a pretty famous picture. If you've been around building science at all, you've seen this probably in almost every presentation. So this is a 3-4-story building in apparently Vermont in the winter time. And so the building is open. It's the white plastic that's surrounding some opening of the building. Maybe they're putting an elevator shaft in or something, so that's open. And what it's just showing is that the hot air is rising, so it's billowing out at the top. That's the high pressure, and the low pressure is at the bottom, or negative pressure. So the air is being sucked in at the bottom. And then anytime there's stack effect, there's also the neutral pressure plane. And we have no idea where that really is most of the time. And sorry about that. We have no idea where that really is most of the time, and it moves also. But this goes back, we'll talk about it later too, in terms of air sealing. Air sealing the top of the building and the bottom of the building is more important than air sealing the middle of the building for that reason, the neutral pressure plane reason. And this just kind of shows the same thing in a schematic instead of a live picture. We also talk about, so what this is saying is it's cold outside. Whether it's cold or hotter outside than inside, it reverses the direction of the flow. So the air can leak in or out at the top or bottom, depending on the pressure outside. And the length of the arrow is demonstrating the longer the arrow, the higher the pressure. So again, it goes back to the neutral pressure plane where there's really zero pressure. At least from the stack effect. There's still going to be wind effect and other mechanical effects going on to the building. All right, so why don't we pause there before we go into roofs and see if there's any questions, Steph.
Scott, there is one question actually back on the balloon framing. You could just cover a few of the sort of common building science issues that we see with balloon framing.
Okay, so what we see with balloon framing is, so this stud here that's a little shy of 8 feet tall now could be, well, it's going to be more than 16 feet. So that's assuming an 8-foot ceiling, right? So this stud is going to start at the bottom of this plate, go through the subfloor, through the wall, through the next floor, and through the next wall, and then this one stud is going to then also terminate then in the attic area. And what happens is what they used to do is then they used to like hang the wall on this, or hang the floors on the inside of the wall. So that really long stud that goes from the bottom to the top is like, it's like hanging a shelf in your house, right? Now the floor is just hung on the inside of this stud, And what that causes, building science, what we're doing is now, if let's assume this is a crawl space, now the air from the crawl space can get into the wall at the bottom, go all the way through the first floor, the second floor, and the second floor wall, and then to the roof. And when we're just talking about stack effect, that's really the issue here, is that you know, it's always going to be cooler or almost always cooler in the crawl space than the attic. So it's like having a chimney in the house. So each stud bay is a chimney that's just constantly moving air from the crawl space through the wall and up into the attic. And air movement, even if there's some insulation in the walls, air will still move in most types of insulation, and it's going to diminish the effectiveness. A lot of these didn't have any insulation in them. So that's, building science perspective, that's probably the biggest concern, is that we just don't have a draft stop. We used to put called fire blocks or draft stops in even an 8-foot wall. I think sometimes it's just to have a place to nail the drywall, but we used to call them fire blocks, and I think it's still required in walls above 8 feet or 9 feet or 10 feet or something, but to have a fire break as a stud. So that's what the real issue is. Let's see if I can. That's what the real concern is here, not having a place for the air to stop against. It's not being able to six-side your insulation. It's also bad for fire as well. That's all I can think of off the top of my head. Any other questions, Steph?
Nope, not this time.
All right. Let's get back to where we were. All right. So a little bit about roofs. Let me check my time. Oh, we're moving along well. Typical roof construction. This was kind of showing a flat roof, but it's, you know, if this is, it doesn't have to necessarily be flat. But so you've got some sort of bulk moisture membrane at the very top. You've got the subdecking here, and then some sort of framing, or this could be a truss, your insulation and your drywall. And what this picture is really showing is that if there is an air leak moving through your ceiling, through your insulation, because most insulation is not meant to stop air movement. That's what your drywall, or one of the purposes of your drywall is, or should be. So that moist air that's inside the house can come up, condense on a cool roof, and then that's like the dew on your mirror when you get out of the shower. Basically, it's the same thing's happening. And if you shower long enough, which you won't because we're in a drought, but if you showered long enough, that dew on the mirror would build up and start running down the mirror. And that's what can happen in roofs. So that's one of the problems in the roof construction with air leakage. And this kind of says the same thing. This is in a cold climate, and in a cold climate, we're in Lake Tahoe or something, you've got additional concerns. We're very fortunate in the Central Valley, at least, where we have pretty low humidity and the temperatures don't get very low. But in a colder climate, that air leaks can cause the vapor can condense on the roof and then freeze on the roof, and then you're going to cause additional problems, ice dams and stuff. So that's really what this is talking about. But we don't have a lot of those in California, or at least not most of us. So air barrier materials, there's lots of different air barriers. That there's a whole list there: drywall, plywood, house wrap or Tyvek, spray foam caulk. All those can be air barriers if they're applied properly. Plywood or OSB can serve as an air barrier if the seams are sealed. All of them have what's called a perm rating, and so like OSB is gonna, even though it can serve as an air barrier, it'll still leak some air out of it. It's not like a tire where it's going to hold pressure continuously, but it leaks slow enough we can still consider it an air barrier. So some are better than others in terms of air barriers. And so these are primarily for ducts, but that's the point, right? Ducts themselves are an air barrier to the house. The ducts are part of the building envelope or the building shell because inside the duct is basically heated air or cooled air, that's conditioned air that's in the house. On the opposite side of the duct, a lot of times, at least the way we build, is going to be an unconditioned space. So you have to think of them as ducts as part of the building shell, no different than the wall. And these are a couple of ways just to seal them. I've also used a lot of duct sealant to seal like top plates in the attic and stuff, just because you can paint it on pretty quick and it works well if you're doing it by hand and not spraying. So air sealing, seal high and seal low penetrations first. So like a can light, second story can light, that's more important to seal than an electrical outlet on the second floor, right? The electrical outlet on the second floor is kind of close to what's called the neutral pressure plane. And again, there could be wind, and wind alters the stack effect. So the neutral pressure plane has less meaning, but there's all these forces acting at once, and it's still going to have less value in the middle of the house than it is at the top, at the bottom. Most of the time when I air seal houses, though, it's just you kind of seal what's easiest first, and then work your way down until you run out of time or money or both. And you also can learn what's the best bang for your buck. Yeah, it all depends. But again, don't forget your HVAC ducts. That is part of the envelope, so sealing those helps reduce air leaks. It's just a blower door we'll talk about later, but the blower door also measures leakage out of the ducts because we don't seal them off when we do it. Shafts and chases, drop soffits, recessed lighting, drop ceilings, all those things should be air sealed well and are kind of common areas that are not air sealed well. Major sources of air leaks, I don't think I can add a whole lot to this. Fireplaces, one interesting thing they say is fireplaces are usually, even if you use them and and close the damper when you're done, the net energy produced in the house is still a negative because of the continual air leaks out of that chimney. So in general, don't use fireplaces, I think is what most people want to do, besides air quality and everything else. Electrical outlets are very small, vent fans are very small, windows are really, in most homes you don't change windows because of air leaks. There's just not that much air leaking out of windows. Yeah, doors, plumbing penetrations, you got to check all that stuff. So here's some top plate sealing. New code in California is you've got to seal all the top plates. But in the existing market, none of these are sealed. So the best way to do it, the way I always did it was I would first remove all the insulation like they've done here, the picture on the left, and then invite all your friends over to come seal all of these, or use some sort of spray foam. Depends, but suck the insulation out first. Best way to seal these, I've done it both ways, and then blow new insulation in. It's usually pretty easy to sell. You show them all the feces that's up in the attic, and most people motivates them to get it out of there. The old insulation, that is. Can lights are very leaky in general. Even again, California code requires what's called IC or ICAT can lights, insulation contact airtight can lights. Airtight can lights are not airtight. It's just a total misnomer. They leak less, I guess, than many of the old style can lights, but they're certainly not airtight. So you want to still seal all the edges of modern can lights. They still leak a lot of air. And your can light, you've got a bulb in there, that's going to be a hot spot, so hot air rises. So it's a perpetual source of air leaks, let alone just the trim around the bottom and the gap between the can light and the drywall. It's never perfect, and nobody typically in construction goes back and seals the drywall to the can light, so that's our job. And in ducts, again, ducts are so important for so many reasons to get sealed and have them done properly. Just for, not only you're wasting energy. If your ducts are leaking 30%, then 30% of all the money you spend to heat or cool your house is wasted. Basically, it's a pretty direct comparison. So that's certainly energy efficiency is one. Depending on where the leak is, if it's a return leak, it could be sucking in air from the attic where those rodents hang out, or just sucking in insulation from the attic. So it makes for worse indoor air quality inside the house. So don't forget the ducts. Just a note on the BPI exam. The BPI analyst exam, there's no duct testing required on that part of the exam, only a blower door, but just touching on it here. And then, like we talked about the stack effect, you want to seal air leaks high and low. Well, you're doing that because what does an air leak need? It needs a pressure difference and it needs a hole. So you seal high and low because that's the greatest pressure difference, high and low. So in a ducted system, the greatest pressure is closest to the air handler. So same size leak right at the air handler is going to leak more than that hole if it's near the very end of a duct run. So start in the middle or start at the FAU, the forced air unit, or the fan, basically, and work your way out. Again, basically, but you just want to seal everything the best you can. And then this is chase. So this is in the attic of a house. This is like a B vent from maybe like some heater, probably in the first floor. And so this is the exhaust pipe that runs up through the second floor, or it could be first floor, and then out the roof. So this is that exhaust. And so what this does is, again, think stack effect, think convection that we've already talked about. Hot air rises. Well, now, and as you can see in there, of course, nobody insulated that wall inside the chase. And so, and of course you need a 6 sides. So that is a wall, that chase that runs straight through the house is a wall that's usually right in the middle of the house that has absolutely no insulation in it. Can't really do much about it at this point when you find it like this, but what you can do is you can put a cover at the top of this. Of course, make sure it's the right material, depending on if that's a B vent, combustibles have to be at least an inch away, so you could do a metal plate there or something, but you want to stop the air movement there at least. So and then add insulation on top of it as close as you can to it. Just to stop, you can't do anything about insulating the chase down below, but you can at least stop the air from going all the way up, like from the garage through the second floor and out to the attic. So you can at least stop it there. Because in that chase, there's going to be other items, and there's going to be leaks all through that chase. Electrical outlets or plumbing outlets, usually chases are used for many different reasons. So do a little plate there and seal that off. And so chases could just be HVAC. Again, it's usually on 2-story homes, 2 or more story homes. HVAC, ducts running through these chases, ventilation, laundry, or combustion. In the summary, and then we'll take some questions, the pressure boundary is it's a monolithic assembly that provides substantial air sealing for an interior area. So the pressure boundary is that whatever's stopping the air pressure. Most of the time, it's going to be drywall and glass, and then maybe the doors make up the majority of the pressure boundary. So any hole in the pressure boundary anywhere is undermining what it's supposed to be doing. Yeah, and then you want to do what you can to mitigate air leaks or infiltration. Stephanie?
Scott, you're good to go to the next section.
Wow. Well, I hope that doesn't mean you all know it already. Okay, so blower door testing. Blower door is a part of the building analyst exam. Not going to talk much about it in a webinar because it's pretty hands-on if you need to learn it. But I'll show you some pictures and we'll talk about a couple items. So what a blower door does is, if you want to use that same analogy of the pressure of a balloon, so what a blower door does is basically inflate the balloon. And so the fan operates at a speed necessary to maintain the pressure. So if there's a leak in the balloon as you're blowing it up, how much air do you have to continually blow into the balloon so that it doesn't increase in size, the balloon, or decrease in size? So that's how it's working. So you get the fan going, it's pumping air in, and it's trying to maintain typically a pressure of 50 pascals inside the building. And there's no reason that it's 50 other than that's just the standard. You could do it at different pressures, but that's the one that's typically used. Blower door can be used to pressurize or depressurize a house. There's sometimes you would want to do pressurization, sometimes you want to do depressurization. Most of the time people do depressurization. The blower door, the pressure of the blower door is not enough to affect animals and birds and people. It's totally safe to run with them in there. It's not totally safe at all to run if there's a fire in a fireplace, of course. But that's the big thing that you have to worry about. But what it's doing is like I said, it's figuring out how much air do you need to continually pump into the house to maintain the pressure. And what that's really telling you is how many holes you got in the house. So it's there with there's a few rules of thumb that you can use to figure out the hole size, and these are very general, but like if you divide your blower door number by 10, that's the number of square inches. That if you took every little leak in the house and put it into one leak, that's approximately, so 2,000 is your number, so you got 200 square inch hole in the house. It's very rough, but it's just it's something that people can, with 200 square inches, if you can convert that to, is that the size of a basketball or whatever, a volleyball or a golf ball, you can tell people this is how big of an air leak there is, and that's kind of why you're there, right, to fix that, make that basketball into the volleyball size hole in there or something, because we never get all of it, but that's essentially what a blower door is doing. Yeah, pretty good. So again, it's quantifying how large the aggregate holes are in the envelope, and that's just aggregate is if you add the leaks from the windows and the electrical outlets and the switches and the can lights and the attic hatch, if you add all those together, it'll tell you basically, it can give you an idea of the size of the hole if you add those all together. And again, it's not scientific, it's just kind of a rule of thumb. It's pretty close though. I've tried it several different times by like opening a window and measuring the square inches of it. But so it gives you something to measure against, and we've talked about the advantages of reducing air leakage. Well, this is a way that you can quantify how much air, how well you're doing when you're sealing the house. so it can track your progress. And you can also use it when you're calculating how much mechanical ventilation is needed in a house. It can be used to aid in that too. So how much continuous mechanical ventilation do you need to keep everybody healthy and happy inside the house? All right. So a blower door is also a really great marketing tool. And I think that's one of the real advantages of a blower door is it's a really cool piece of equipment that you can put in a blower door, and people, when you turn it on, they can actually feel the air leaks and they can start to understand why you're there. So I think it's really a great marketing tool. We don't really need to do it at test in because we know that the house is leaking a lot, but it does give us something, so it can help us track our progress. So anyway, that's kind of, yeah, anyway, great marketing, and it is on the exam. And we can, when we get to Stockton, we can do a little practice of blower doors if people would like. But most of the hands-on field training in Stockton is going to be about combustion equipment, but we can certainly take a few blower doors and practice while we're there if anybody would like. Steph, do we have any questions?
Nope, we don't at this time.
All right. All right, thermal boundary. Thermal boundary is all about insulation, so that's what this piece is going to be talking about, and where that thermal boundary is located. So like here, this picture has in the attic a thermal boundary at two different locations. On the left side, it's showing it as in the ceiling, and the right side is showing it in on the underside of the roof itself. And then like the crawl space area there, you know, we got a thermal boundary in the crawl space that then goes down the wall and into the basement. But that's all thermal boundary issues. So the thermal boundary, it's the physical separation from the conditioned to unconditioned space. It's all about insulation. Insulation should be present and continuous, and it should be aligned with the pressure boundary, which we spoke of. Different types of insulation. Fiberglass, there's fiberglass bats and there's blown-in fiberglass. You never get the pink guy, what's that guy, to come up in the attic and blow it in. But the fiberglass bats is what most people do in walls. They are almost impossible to put in correctly, and I don't think these are even installed correctly in the picture. And then there's the blown-in fiberglass too that you typically see in the attic. Cellulose, it's my favorite mostly because there's hopefully a lot of recycled content in it. There are advantages and disadvantages to both cellulose and fiberglass, just like everything in life. So cellulose you can blow it in the attic. So the disadvantages to cellulose in the or anywhere is that it holds moisture longer typically than a fiberglass. The disadvantage of the fiberglass is that air moves through it much easier, so it loses its effective R value too. So you can blow in cellulose in the attic, or you can dense pack cellulose in the wall, like that picture there. So that cellulose is blown into the wall. There's a little moist, and that's what makes it stick. You leave the wall open for like a day. It dries enough, you put your drywall up. That's dense pack cellulose. So other types of insulation, there's expanded polystyrene. So that's what you find. The top picture is just a styrofoam cup. You know, that's what we call styrofoam. Expanded polystyrene is styrofoam. It's used a lot still in industry. It's used in continuous exterior insulation now in most new construction. And part of the bad part of styrofoam or expanded polystyrene is it's still permeable to liquid, which is what that picture is showing. And then there's extruded polystyrene. A lot of times it's more expensive, but it does not hold moisture. So it's a closed cell foam, so moisture can't get into it, and it can't stay in general if it's made properly. So I've installed a lot of extruded polystyrene in crawl spaces, stem walls, and crawl spaces in wet areas. It's great for that. And then there's polyisocyanurate, which is that top picture, and that's it's kind of got the same texture of styrofoam, although it's a little more fragile. It's expensive, but you've got better R per inch value out of it, so that's why it would be used sometimes. Even though it's a little more expensive, it has better R per inch. And then there's vermiculite. People don't use it anymore, but it's worth talking about because we find it a lot in old homes, and it's just little particles of something. I don't really even know what it's particles of, but a lot of times there's asbestos found in it. I've seen it in attics, I've seen it in walls, but it's like little pellets of stuff. You poke a hole in the wall of that stuff and it just all drains out. But it's out there. It's something, if you see it, you want to be cautious that it might contain asbestos. So treat it as if it did. And then spray foam insulation, that's kind of all the talk in building science still for like 10 years now. There's so many great things about spray foam insulation, the R per inch, and spray foam insulation is a generic term. It's like talking about soda pop, or I don't know. There's all different types. There's closed cell, there's open cell, there's different manufacturers. There's some that's got like a soy, they call it a soy base, but there's a little bit of soy in it. Most of them are all largely petroleum. But the advantage of pretty much all spray foams is that it can serve as a air barrier and insulation in one. Even the ones that are open cell, which means air could get through them and water could get into them, it's still an effective air barrier, kind of like OSB is an air barrier, even though air can leak through it. Yeah, and the one thing I used to hear a lot, people would say, well, yeah, but you know, if you spray foam in my walls and the house burns down, it's really, you know, bad for my health. And it's true, but you also shouldn't be in your house while it's burning down. That's my tip to them. Leave the house if your house is on fire. Doesn't matter what's in the house, it's all bad for you as it's burning. So thermal boundaries, ghosting. So what both of these show, what the gray is called ghosting, and what that means is it shows where air is leaking. So let's use the one on the right, that kind of rectangle piece there. It perfectly matches, as you can see, that rectangle piece on the floor of that stud bay. It just shows that there's been air leaking through that wall probably for many, many years. And it's a true sign that your insulation is not doing as well as it could if you did air sealing. So just air seal that rectangle there. You could put it back down. You could use the same insulation, and it's going to be a lot better. Ghosting, it's a less obvious picture of ghosting, but anytime there's any discoloration in the insulation, that's just showing the air has been moving through it. Insulation's a great air filter. And that's basically what it's doing, is filtering the air for you. So insulation, it slows heat loss or gain by creating small pockets within the insulating material. The trapped air is really the insulating material. It has a really good, air itself has an R value if you can keep it from moving. Moving air is called convection or convecting. So if you can keep it from moving, air is pretty good insulator. So that's what the goal of most insulation is to stop air movement and trap small pieces of it. And again, the air moving through insulation decreases the R value of the insulation. R value is just the measure of the resistance of heat flow. And most insulation is not designed to stop air movement. Like a spray foam is, but none of these others are. Their intended purpose is not to stop air movement. So R factor is a measure of the ability of insulating materials to resist heat transfer. R value is the R factor of the insulation multiplied by the amount of the material. So we typically talk about an R value, but the R factor is the rough terms that I like to use. Like wood has an R value of about 1 per inch. So a 2x4 stud on the 4 directions, so that's 3.5 inches, would have an R value of approximately 3.5, right? So the R value of the stud is 3.5. R factor is 1 per inch. So R value is just temperature. You can calculate it. It's pretty simple if you can just measure it. You can see what the R value of a wall is yourself. It's pretty easy to measure. But R value is really just one factor about insulation. And the other factors we talked about last time are conduction, convection, radiation, and air infiltration. I guess we talked about this time. But so R value is a form of conductive. It's a measurement of how easily energy is conducted through the wall. But it can also move by convection. That's air leaks, air infiltration, and then radiation through the wall. So U, a lot of times, U is typically, the U value is typically used when we talk about windows. I think it's interesting that we use U value for a window and R value for a wall. And I always think that we do that so that people don't realize how lousy their very expensive windows are. So like if you've got a wall that's an R13 wall, maybe 1 inch of continuous exterior insulation. So you've got a R value of the wall, say R15 or something. Your window, if you have a U value of 0.3, which is a pretty decent window, the R value of your window is actually only 3. So anyway, just kind of a little bit of a side, but R and U is just the reciprocal of R. So 1 divided by R equals U, 1 divided by U equals R, and so it'll tell you, you can go back and forth. But windows always use U factors. Wall assemblies, most other things use R values. So U values tells you how well it transfers energy through it, right? And R value tells how well it stops it, basically. Oh, in my example there, if the U factor is 0.5, the R value is 2, right? So if your window has a U factor of 0.5, your window actually has an R value of 2. Pretty lousy compared to your wall, typically. Okay, so when you're identifying insulation, you're going to look for the type, fiberglass, cellulose. Try to figure out the R value, and usually that's going to be from a table. You want to see how well it's conducting, or the condition of it, of the insulation, the quality and the quantity. Not the quality and the quality, but the quality and the quantity. So the depth, typically, or the thickness. Stephanie, I'm sorry, I'm a little sick. I need to run. Can you think you can handle questions? And I'll be back as quickly as I can. I just need to grab something.
Yes, no problem, Scott.
Thanks.
Yep. If you have any questions, please feel free to type them into the question box. I do have a few questions that I can handle while Scott is out. One of them is, what is the best insulation to use for walls when there is existing drywall? So this would likely be in a existing building. Typically, this would probably be a blown-in cellulose. This is where typically a hole would be cut in the exterior of the building, and blown-in cellulose would be blown in to the wall cavities. And then that hole that was cut would be patched up. And there's another question asking about what is the best insulation to use for the interior walls touching the garage. This one I might have to defer to Scott when he gets back, but if it is for new construction, I would probably have to go with Scott's suggestion before of the existing of the blown-in cellulose as well. But he might have some other options when he gets back. For now, that's all the questions I have in the question box. If you have anything else, please type them in. If not, we'll give Scott just a minute or two, and then we'll restart the webinar. Apologize for the delay. I do have another question. It's about the PowerPoint from the presentations being sent out afterwards. We won't be sending out the actual PowerPoint, but we will be posting this presentation to the YouTube page that Scott mentioned at the beginning of the presentation. If you do a Google search in YouTube for PG&E Multifamily Upgrade, you should be able to get to the website very easily.
Okay, I'm back. I apologize.
No worries, Scott.
Okay, hopefully that wasn't too long.
No problem.
All right, so let's continue on. There's not a whole lot left. We got 20 minutes. Okay, so insulation, more is always better in general. This is, I think it's just a great picture of something I found in this multi-million-dollar house on a golf course in Long Beach, I think it was, where owned by a famous architect, and the interior is immaculate, but the attic looks like every other attic, right? They know that the people don't go up there and look at it, and they paid for some insulation, so they gave them some insulation, but when it's not installed properly like this, it's just not doing much good. Its effectiveness is greatly diminished when you don't install it properly. And this is the same house. This is in the attic, so I think it's great. Somewhere on one of those it says that insulation is intended for crawl spaces only. But they paid for insulation, so they threw insulation in the attic. But not the right way to install it, of course. Effective insulation, you don't want any voids, which is like essentially a gap. So you don't want any gap between the insulation and one of the air barrier. So we talked about six-sided insulation. The previous picture, although that's flat and in an attic, so the sixth side doesn't matter as much, the sixth side, but you definitely want the in contact all the way around the stud bay. You want the vapor barrier facing toward the interior in a hot, dry climate. It is climate specific of where the vapor barrier should go, or vapor retarder. It's actually not a barrier, but it's a retarder. An air-sealed cavity or surface. So ideally, every time you put a piece of insulation in, whatever cavity that it's going in is completely air-sealed. So if you're doing a stud bay, every seam, you've got 5 sides of the stud bay there. Typically, when you put a piece of insulation in, you could caulk the seam of all 5 of those sides, and then when you put the drywall on, you could caulk the face of that before you put the drywall up, and then you would have a completely sealed cavity. And of course, penetrations like electrical penetrations that go from cavity to cavity down the wall, sealing those is also a good idea. Again, you just want to minimize the amount of movement that air can have in your wall. But California code is at least at the top and bottom too of the walls are air sealed at the attic. So at least if you can get top and bottom, it helps. So air sealing and moisture control just helps your insulation do more, or perform as it's intended to perform. Okay, thermal bridging. Thermal bridging is a term used in building science a lot, and what that means is heat energy likes to travel via the way of least resistance, just like water flowing down a hill, right? It's going to find the path of least resistance to get down the hill. Your heat is going to find the easiest way in and out of your house. So what the IR cameras are showing there is, like the top one is showing where all the thermal bridging is occurring. Each stud is a thermal bridge. We talked about it. The stud bay, if it's a 2x4 wall, will have an R value of about 13, but the stud itself will have an R value of maybe 4. So the path of least resistance is it's going to go through the stud bay. So it doesn't mean your insulation is useless, but you're not getting, there's basically gaps in your insulation, so it's short-circuiting through the stud. So there's talk about thermal bridging, and that's when we talk about continuous exterior insulation. We would put in like a styrofoam insulation or on the exterior of the building on top of the studs, and it just would help add insulation on top of the wood and the cavity, the R13. So it just increases dramatically the R value of the whole wall assembly. R values can be added together, and U values cannot. So everything has an R value. So in a wall assembly, let's say there's stucco on the outside. Oh, here, my next slide has it. So R values of a wall assembly. So you've got the sheetrock. Half-inch sheetrock has an R value of about 0.45. This has a foil face foam insulation of 7 per inch, right? 5.5-inch fiberglass installed in good condition should give you an R value of about 14. That's low, but that's anyway. Let's just go with that. Half-inch exterior plywood also has, the wood siding has an R value. You can add all those up to get the R value in that spot of the wall. So that in this example, in the middle of the stud bay, there's an R value for that of 22.94, 23, right? And then we can convert that to a U factor just dividing by 1. So 1 divided by 23 is 0.04. So you can add R values, you cannot add U values. It's just a mathematical property. So keep that in mind. Typical written exam for the BPI building analyst is they'll give you, maybe they'll give you a couple R values and say what's the combined U value, right? So you just need to add the R's and convert to U, or some combination of that. So make sure you understand that if you're going to take the exam. And the other point to make is that that is only the R value of that point in the wall. We talked about the stud in the wall. That's the the wood member that goes vertical in the wall. It has a different R value, so it would have 5.5 inch. So maybe that has an R value of about 6 right there. So you place that 14 with a 6, and that's the R value of the point in the wall right where the thermal bridge is happening. So take it. So we got like an R value of about 15, right where the stud itself is in this wall. So still pretty good, but not as great as the rest of the wall. So there is a way. I'm going to cough. There is a way to figure out an average R value for an entire wall assembly. We won't cover it here. That's all our softwares, EnergyPro and stuff. They've kind of they have framing factors, and they will figure out the average R value of the entire wall. And so we don't need to do that math anymore. So when we talk about adding R values in parallel, that's just kind of getting the average R value of the entire wall. It takes into account the thermal bridging through the stud, like I just talked about. It gives you the average R value of the entire wall. Mathematically, it's more complex, and we don't really need to do it here. Like I said, it's done for us in most softwares. So summary, a bunch of different insulation types. Polystyrene, polyisoisannurate, extruded polystyrene, expanded polystyrene, lots of different insulation types. Being able to identify at least fiberglass from cellulose is important. I think most foams you're going to know if it's a foam. So if you can identify foam from cellulose from fiberglass, that's important. And that's usually what you're going to see. And then thermal bridging, hopefully. So at this point, Stephanie, you got any questions that you didn't handle at our break?
Yes, we do have a few questions. One question is, what do you recommend, what type of insulation and installation method do you recommend for scissor trusses?
Scissor trusses. Well, the age-old question, it depends. It depends on how much insulation you need. I always like, depending on how much insulation you need, how much thickness you need. If you can fill the cavity, you probably don't want to. It's too expensive. At the very least, it's great to do the best way. Well, maybe the best would be to fill it with the spray foam, but it's pretty cost prohibitive. A lot of times what I would do is I would do a closed cell spray foam and do just a thin layer of it, and that serves to stop my air movement. And then I can just fill the rest of the cavity, or depending on how it's installed, with like a spray and cellulose. Again, cellulose is kind of my favorite.
And Scott, as a follow-up to that question, how would you do that if there's drywall up?
If there's drywall up and you have scissor trusses, I mean, how would you do? Well, you're not going to do the spray, the closed cell spray foam. Again, it's called a drill and fill. And I would talk with my insulation guy and troubleshoot it, but I would guess that it would probably be a drill and fill cellulose spray-in that you would do.
Great, and we just have one more question. For cold climates, is continuous insulation best on the exterior or the interior?
Okay, so I have to think through the physics in my head. I think in general it doesn't really matter where it is in the wall. I think the exterior is easier to install, and you get better coverage on the exterior because you don't have interior walls in your way. There's no there are some products that have insulation. The drywall is basically the insulation arrows gel, is what it's called, I think. And I've seen that used in some high-rises where you can't do the exterior. But I'm pretty sure there's no real, I would have to think through the physics offline, but I think your exterior is going to be the best way to go, depending, irrelevant of the climate.
All right, that's it for now. Just want to let you know that we have about 6 minutes left.
All right, great. I cut a lot of slides out of these, this last bit, because we only got 8 slides left, so we'll wrap it up here. The building assembly. So the wall, we've talked a lot about this. Maybe the slide should have been a little earlier, but there's lots of pieces of the wall assembly. It's not all about the R value, I guess. And that's maybe just the point of this slide. The wall is not all about the R value of the insulation in the stud bay. There's a lot of pieces that go into it, and thinking through each one of those is important, and what it does and its purpose and where it should go. Windows. So there's the glass assembly, which is the glass, dual pane. Hopefully you're going to have a spacer between 2 pieces of glass. And then, so this is just kind of the components, because knowing a couple of these words is important. The sash is the glass assembly plus the frame. So it can be movable or non-movable, operable or fixed piece of glass, but there's, if it's vinyl, it's going to have a vinyl frame around it, or wood frame around it. So all of that, the glass and that, is called the sash. And then there's a frame that surrounds the sash. So the sash is a frame and glass, and then there's a frame that the sash goes into. And then we often talk about rough opening as well. A rough opening is what the framers gave you to put a window in. So in EnergyPro, what we should always be using is the rough opening, because that's the opening that the window is going in. It's going to be larger than the window, or the window wouldn't fit. If you're in the field measuring it, you need to take into account that the drywall is there. So if half-inch drywall, your opening is going to be at least an inch in each direction larger. But that's the rough opening. That's the where's the wood? What's the size of the wood in that wall for your window? Doors. Doors. There's really not any great technology for doors to do super duper great building science doors. Doors are doors. There you can get some, there's obviously hollow core doors, which are supposed to be on the interior, although I see them on exterior doors. You can get insulated doors with slightly higher R values in the doors. Solid wood doors are also there. They can also be rated, and you can get a U factor of them. But I think the main reason why we don't hear a lot about doors and high performance doors is the area of all the doors in the house is pretty darn small compared to windows in the regular wall. So greatly increasing the R value of the door doesn't give you a whole lot. What you do want to pay attention to on doors is just the weather stripping and the seal. The airtight seal in that door is probably the most important thing to pay attention to. Not necessarily the door itself. If you want to dramatically improve the performance of your door, don't use windows in it. Windows are always big leaks in the door. So in doors, you want to check for gaps between doors and the stop, the weather stripping. You know, check the swing of the doors, and it's all about the weather stripping. You know, if you do one really great use of a infrared camera is just with your blower door running and your door closed, you can check for leaks in the weather stripping around the door. You can see it really easily, and you can adjust your weather stripping. That can be an important one. So building assemblies, there's lots of different components to the roof, as in everything, and I've used a lot of terms in this, like studs, and there's studs, there's sill plates, there's king studs, there's trimmers. Those terms we're not going to go over, but you should know for the exams. Know what a rim joist is. Those are just some basic framing terms that you should use. Sill plate, top plate, know what those are. And this picture shows a few of them. The ridge board up top, this would be the rafter, and then this could be the rafter ties if it's going, you know, it's up off the ceiling, or if you had some fancy ceiling, it could be the actual ceiling joist, but typically it's not going to be. So, but point is to know what those are, what all the components in this wall are, like the header, the trimmer, the king studs, just normal stud, double top plate. Know what all those are called. Oops, sorry about that. HVAC platforms in attics are interesting, right? People usually just stick them right on top of the ceiling, but you need space for insulation under there, vent baffles, ventilation, and just of the attic space. If you have a vented attic, make sure it's appropriate. Building assemblies, roofs. Oh, we're almost out of time. Again, just know that it's a whole buildup of materials in your roof assembly and ceiling assembly. And that really does it, and we can answer questions if there are any.
There's no questions at this time. If you do have some questions, we'll stay on for a few more minutes, so please type them into the question box. In the meantime, I'd like to remind everybody that we will be posting this on the PG&E Multifamily Upgrade YouTube page. If you do have additional questions after the presentation ends, feel free to give Scott Blunk or Mike Maroney send them an email, and they'll be happy to answer your questions. Anything else from you, Scott?
Nope, that's it. I just want to let you know next Wednesday will be another EnergyPro webinar, June 10th at noon. Hope to see you then, and then we'll continue this series on June 17th.
Great. On behalf of the PG&E Multifamily Upgrade Program, I'd like to thank everyone for attending, and also Scott Blunk for presenting today. Please remember, after the webinar is closed, fill out the brief survey, and if you have a BPI certification number, feel free to enter that in, and we will report this for your continuing education credits. Thank you, everyone. Have a great day.